Starting clear up your desk from stuff. Computers, please. Sorry, I don't remember your name, but hello? Computers,
I'm
cell phones, what?
and I'm taking notes.
Well, I mean, unless you do it by hand, then.
Yeah.
Yeah, so if you're writing with a pen, that's fine, as long as it's, as a substitute, I suppose it could be tolerated if you were not get distracted once again. So a tablet that is used as a piece of paper. Okay. Nothing else. Okay, all right. Okay, so we're on. And okay, so this is where we are right now. And that is the last example, exponential growth. So it does not have to be about motion necessarily through physical space, but could be motion through any space of any quantity changing. And so this is the population, which happens to be the basic population model, is that the growth of the population, the increment of the population is proportional at the bottom to the current population. Once again, every, a city, for example, for every 1,000 of population have 10 babies born, for example. That's the proportionality. If you have 1 million, then you have, for 1 million, you have 10,000 babies, or if you have 2 million, then you 2,000 or 20,000. Okay, so proportionality, no matter what the size is. And the key is how well things are going. And the presumption is the death is also proportional because it's more happens in a kind of a natural state. So not taking into account things such as age and so on. And but basically accidents of life kill people. And so that simplified model produces this is really simplified equation. And then from that equation, it's also proportional to the period of time, because once again, if you proportionality, number of babies per year, per 2 years, double. Okay, so that's multiplication. So that's how we created this model. And then we did some, this is the data. Okay, so the data then visualized either by coloring the cells or the 3D surface. It's what it is. So for each x, y, well, in this case it's t and y, t time. Second, am I using? Okay, so this, I guess it's a typo here, right? Here it is over here. That's a typo. So one variable is t time, the other variable is y. And so our solution that we are after would be how y depends on t. So how population depends on t, which has not been solved yet, but the data is here. And they remember a previous example was how we can climb this ladder. And as population grows, the color becomes deeper and deeper, and we grow faster. So accelerated growth is to be expected from the model. So that's if you like, that's the qualitative analysis. To begin with, k positive, we have growth. K negative, we have decline, right? So the change is positive when k is positive, change is negative when k is negative. Okay, so going down or up, okay, increasing, decreasing, and then if you look a little bit deeper to the next level, that's like a level 1. If you go to level 2, accelerated growth. You have grown and you moved on to the next level, and then the population is bigger, therefore the growth is bigger. Okay, so not only observe first derivative, those two numbers, as a matter of fact, what they're in reference to, first derivative growth or decline, and second derivative is whether or not there's acceleration. In other words, acceleration, what's in the language of calculus, what do we call it? Accelerated growth. What's the way to describe the graph? Concavity, right? Concave up. Right, so it looks like this. That's acceleration, straight line acceleration without growth without acceleration, and this is accelerated growth. Okay, so nothing but what we say qualitative analysis. Okay, so and then we from that point on, it's growing, but it could be quadratic, right? Think about accelerated growth could be quadratic. Why not? Nothing stops from being quadratic. So how do we know? Well, at the very least, we can do the modeling, the simulation thing. That's the formula directly come from our equation over there in the box. And so the growth delta 1 plus 1, the next stage is progressed by that quantity. The right-hand side of my equation, ky delta t, becomes the increment. And so we move on every time we update our y. And therefore, we know where which way we're going to go. What the population will be the next unit after the unit of time has passed. Okay, so delta t is chosen. The numbers here is delta t, h is 0.1, k is 0.2. And this is the computer builds you one particular example, one particular setup, but the initial conditions vary, as you can see. But all you see what we discovered by qualitative analysis, growth period first, and secondly, accelerated growth. If you build more, then you discover also a decline for the decay. K negative means population decay, which could be naturally population decay in the literal sense, population of either people or animals, and then decays towards 0. Okay, so there are more deaths per thousand than births. Okay, so that's the decline. You can see they diminish towards 0. There are other examples. Exponential growth. What else is modeled with exponential growth or decay? What else declines like this?
Radioactive decay.
Radioactive decay, that's right. And probably you can, if you want to look into physics, you probably can see the argument that is similar to population. So you have this many billions of particles, and they're fly away into cooler into outside of that material, and then it declines in mass, right? Decays. Okay, so you can make a case that the dynamics is similar between the radioactive decay and population decay. Okay, so that's the simulations, give us the big picture, all possible dynamics are described here. Then what we did, we also created the difference quotient, which is the same equation, only we divide by delta t. Okay, then we take the limit, and then that's when we discover that actually the equation is not too bad. It's not. So y prime is equal to y. That's the differential equation that we need to solve. The solution is, however, is not straightforward. Is not a method that we deployed last time. Just integrate. How do you need to get rid of differentiation on the left? Okay, so you can just integrate to get rid of it, and so I do. But unfortunately, you can see what happens. While differentiation disappears on the right, on the left, on the right, we have integral appears. And so we have an integral of an unknown function, which is really, so we are pretty much in the same place we will. So we need to find y from a certain equation, and it is given indirectly. So either derivative is expressed in terms of y itself, or the integral is expressed in terms of y itself. Either way, it's not the solution. It's still an equation, meaning that it is indirect. So it is possibly defines the function directly, so it's there, but it is for us to find it. And the only way that we are actually able to do it at the end, what we did last time, is actually remember differentiation rules, differentiation experience, calculus 1. You know that there's only one function, well, not only one, but we certainly want to remember one function, the derivative of which is the function itself. Okay, so that's the once again experience and remembering prior experiences. And then the question I actually ask all, are these all? Can you think of other functions that equal to its own derivative? I decided k equal to 1, so to keep it simple. A function is equal to its own derivative. Et, what else? You can try to use these pictures to guess this, because this is one solution, but then there's another one. Looks kind of similar. What do you think is the relation between those curves? Guesses would be
Plus a constant.
no. Plus constant is a shift. You can see that's not a shift. Right, so if you take, here, all of these go towards zero, by the way, right, so, it's not gonna go towards zero anymore. So what do you do with the graph of a function that goes towards zero, so that it still goes towards zero? You don't add, but multiply. Okay, so a whole family of functions then is possible solution depending C positive or negative. We have above or below producing all possible solutions right here. So that's the way to solve an equation is to find all the solutions that we just did. Okay, including C equal to zero, which is constant. So as you can see, that answer that this default answer for the integration plus C, it's not working, but kind of does in slightly in a different manner. So it's in an unpredictable manner. So it turns out to be multiplication. So so we'll deal with that later. At this point, we modify the problem. The description is modified because now it's called limited growth. Okay. So the rate of growth of the population is proportional to the current population. That's the statement that we already had. And now into the remaining population of the total that can be sustained. Okay, it's in a jar. So there's a ceiling beyond which the population will never grow. Okay, so how does it stop? Does it run in and stops? No, it sort of they already start feeling hungry as the limit is approached. And so what's going to happen? Well, you can guess what's going to happen before writing a formula. You can guess how the population behaves as it starts to approach the limit. What's going to happen? Based on this proportionality. Well, if you don't see, well, that's right away. That's the point of the whole thing here is verbal description will not solve you the problem. We know that. So translated to mathematics and things will become clearer and clearer. If not, we once again will do modeling or simulation and we'll know the answer to this question. So what does the graph look like? If you cannot see right away, well, that's what it's all for, right? So so in other words, T, suppose the total possible population is T uppercase. Okay, and then so then there are two coefficients of proportionality in addition to delta T is this. Y, so proportion to the population, so it means that there is still double, if you double the population, you double the increase. So the higher the population, the higher it grows, but also we have to take into account that if we also have approached the limit, then how close we are to that limit of the population, that will bring us down. So it's T minus A. Okay, so it will be, it is actually, might bring us, well, actually, it's not going to bring us down, does it? First of all, let's convince ourselves that this is a good model. So it's proportional to the remaining population, which is Y, and then to the population, which is Y, right? And to the remaining population, that T minus Y. So Y is current population, Y, the maximum population, T minus Y. Okay, so if we're convinced that this is a good model, then we can predict from the formula what does the graph look like. Once again, qualitative analysis. Qualitative analysis. After all, the rate of change is on the left. Right. So will the population decline? That's really the answer. In our model. No, because why not?
Depends.
Because this thing can never, if K is positive, right? So it's growth of population. This can never be negative, right? Y is the positive population, T minus Y. We are not outside of the jar, we're in the jar. So the population is less than T, which means that T minus A is positive, which means that there will be always growth. But we now expect that growth will not be accelerated anymore because once again, beyond this qualitative analysis, we can ask ourselves, it's the ceiling. It's literally a ceiling, and so, well, how does the growth, so once again, there's a growth, can you possibly grow into a ceiling? What can happen?
You're just slowly approach it, you won't have.
Yeah, what's the word?
Asymptote.
Asymptote, yes. So it's a good analysis, equality analysis, what I call it, and that's a very good exercise. But the point is that what follows is that maybe we don't have to do it this kind of a trying to be insightful, but rather just brute force. We'll form as you can see the formula and just plug it in and see and play with it and run a few simulations to see what it looks like. Okay, so ky t minus y delta t, so delta t would pick delta t over here. I choose delta t 0.1. I choose t is equal to 1, so that we actually speak in terms of proportions. So population is either from 0 to 1. Okay, so proportions, and then this is what the function looks like. Okay, so that function, what is plotted here is this function is plotted here. So once again, by coloring. In the previous example, we had a white, pink, red, and here, as you can see, it's white, pink, red, pink, white again. So in the beginning, the growth is slow. Why? Because the population is low. At the end, at the top, why the population growth is slow? Because there is little room left. So that's a kind of symmetry that you would think probably to observe, but we already see it, right? So at the bottom, when the jar is almost empty, is the behavior is upside down. The population, the behavior of those bacteria when it's almost full, almost empty, almost full are symmetric kind of, but moving in the opposite. Yeah, upside down basically. Okay, so once again, that's a formula. You can write it out. This is the actual formula at the bottom. Okay, so slightly simplified. So once again, you update your population every time, and the t is equal to 1, delta t is equal to 0.2. So all the t is known to, so all the formulas are known, and then you progress one line to n plus 1, n plus 1, and have a sequence of population if every single number is specified. So not only specify these three parameters, k, t, and delta t, but also the initial conditions. So your sequence knows where to start. So it's actually 4 numbers. Okay, and so once that is established, this is your solution. Once again, running through that field of colors, field of colored numbers. Okay, so you can see slow growth. You can see the fastest growth in the middle. Okay, and then slows down as it approaches being full. Okay, so so then as you can see, you want to expect the small population when everything is still free, sort of, it's almost the same growth as before, right? Almost exponential as we just saw in the last example, and then it asymptotically approaches to the state of being full. That's what on the other end. Okay. So once again, you can do it, and you should do it by hand. I could have certainly done that with this picture on the left. So if remember, every number represents how much it's supposed to jump. So if I start here, I jump and I am at 0.1, and the command is go up by 0.4, except it has to be multiplied by the period. So I will jump, and then I jump some more, and then I jump some more, and then I jump some more, and then my jumps become smaller and smaller and smaller, and then until they kind of slow down. So you can do it by hand. But it's more productive to actually write it is Excel, so it's not really writing a program to speak of with it. So it's it's productive, it's educational. But this formula is literally plugged in. I have a formula of this one. There's a formula somewhere, but certainly rewriting this formula into a spreadsheet wouldn't be a problem. So you repeat it, and then actually from left to right, and then this is just plotting once again with Excel produces this curve. Okay, so exponential growth in the beginning, exponential decay at the end, also known as the S curve. So known as the S curve, as well as the logistic model of growth. So if 1 is not enough, it's the computer. So you just tell it do it rather than 1. You tell it do it 10 times. Okay, so as you can see, yeah, the behaviors in the beginning is asymptotic, at the end is asymptotic. So you can actually write, if you, F is your population, you can write F goes to 1, in our case, as T goes to infinity. Plus infinity. Okay, so that's how you would use calculus language to describe what you see, even though it has not been proven. It is, you can make an argument, so you have growth with a limit, what's gonna happen? It will have, inevitably, it will be slowing down, and therefore that's exactly what asymptotic behavior is supposed to indicate. Okay, questions so far? So once again, setup, the hard part, the quotes analysis a little bit, then simulations, several. We have the whole picture is right here. And then finally, the analytic solution, if possible. Analytic solution, in other words, we are getting rid, remember what that is, switching from difference quotient to derivative. It means delta t goes to 0. What it does, it disappears from the picture. Okay, so things simplify, and then you hope that you might be able to figure out what this is, and unfortunately, there is nothing there. Okay, so it was hard enough to y prime is equal to 3y to solve that equation. We already solved y prime is equal to y, and remember that the exponential function. This one is slightly harder to actually remember, even though you must have done it before. But nonetheless, remembering that that's kind of a differentiation you've seen before is challenging, and this one is really is way by far more challenging to find out what is the y could be here. And once again, there is no method that you can for now that would allow us to do that. So if you try to integrate, once again on the left you'll get y, on the right you have this integral of the function that you don't know, so you cannot complete the computation. So we are pretty much stuck in the analytic part fails. Analytic, for at least for now, but it is something to be expected. Analytic study of the differential equation or the model fails. Okay, so that's then all we've got right now. Okay, that picture and those simulations. Okay. Describe each solution using linear calculus. Once again, it's increasing, decreasing behavior. Remember the basic things: increasing, decreasing. Concavity, meaning the second derivative, and possibly in the asymptotes. Okay, so that's okay. That's some exercises. Actually, this is another model. In addition to radioactive decay, here's cooling and heating. Goes all the way back to Newton. This is the description. The rate of cooling is proportional to the difference of the current temperature and the room temperature. So as you can see, it is slightly simpler than the last model because there's only one quantity there on the right hand side. Okay, so once again, the closer, but you can see that what we're saying here, as the temperature is closer to the room temperature, the slower it is changing. Right? That makes perfect sense, and so it made sense then. And so once again, verbal description of the dynamics, whether it is cup of coffee hotter than the room temperature, which is cool soda that is cooler, doesn't matter. The description still works because when it is higher, the rate of cooling is then the temperature is higher than the room temperature, and but we speak of cooling, so it means that they would have to have a negative sign here. Okay, so when the difference is positive, we have to go down. When it's negative, we go up. But it is what negative numbers are for. Okay, so R minus Y is that temperature. The R is the room temperature, and Y is the current temperature. And so our rate of change of the temperature. Once again, T is in the denominator because how far it's going to cool down depends on how much time has passed. Okay, so as you can see, once again, equations very similar case that once again unspecified proportionality coefficient, and there's only one coefficient, very similar to the last one, right? It looks maybe a little bit, except for the sign, it is the same term as we had with the population, except population goes in the opposite direction. So the dynamics is to be expected to be different. And somewhat, but otherwise, that's, we took the description, rewrote it in terms of this, of y, okay? So, all right, so, let's confirm it here. Here, case assumed to be positive. Once again, once you see equation, you can try to do qualitative analysis. And then once again, confirm that when the temperature y is lower than the room temperature, the right-hand side is positive, right? Which means that there will be growth. So y is less than r, we have growth. Y is larger than r, right? So that coefficient is negative, the right-hand side is negative, and therefore we have decline. Okay. So once again, it is a good thing to pull out some understanding of derivatives, what it amounts to, from calculus 1, and predict what's going to happen without any computations. But and we're going to do quite a bit of that. But also remember that the brute force is really also very effective. It's the only thing, the problem with the computers is that you have to specify all the numbers. This is a very, even though imprecise, it's a very broad description, right? That every situation is taken care of. There are only two cases, and you already know very specific facts about them. When you do go numerical, you have to pick all that you have to. R have to be specific, K has to be specific, delta T has to be specific. And so you're running only one instance of the whole thing. It is very productive, however, to once again, this is my right-hand side. Okay, so low temperatures produce growth, red. High temperatures produce decline, that's blue. And somewhere the temperature itself, R is equal to 0. So hold on, that doesn't, I don't think R is equal to 0, maybe. It seems like R is equal to actually 0.5 unless it's a typo. Well, we'll see next. So the picture seems to suggest that the room temperature is at 0. So if at 0.5. So if you are, or 5.5, if your temperature is 0.5, then naturally there is no change in temperature. You have constant solution, as you can see. So there will be growth from below and there will be decline from above. That's what qualitative analysis tells us. So let's confirm that by running the our formula. Same formula we form, it's the same way. So this is the same, this is varies from one model to another, but otherwise delta T is also present, K some kind of specified is also always present, and of course Y, the current state. Okay, so we spoke of locations, we spoke of populations, we're now speaking of temperature, okay, and so different quantities of different nature, but the otherwise everything works very similarly. Okay, so and then we carry it out. Here we go. Yeah, it appears to be R is equal to 0.5, not 0, so it's a typo. And so once again, depending, it's exactly the same equation, same quantities, but the initial condition either starts, initial state is here or here, and then it either higher or below or lower than the room temperature, and then the behavior, as you can see, very nicely approaches it as you would expect from an object put in the environment of where there's such an exchange. Same with the radioactive decay, right? So once again, it's literally those, if it's hot coffee, those particles are flying around or within the coffee, and then once in a while they die by flowing out of the coffee. And so they do it in the proportional manner, because the hotter it is, the faster they're moving, right? And therefore likely to jump out of the coffee. Okay, so that's what causes cooling. Okay, so so these are the two. You can do more. Okay, so if you like, once again, something cool, something hot, so any questions about this? So once again, the answer is not one solution typically, but all the possible solutions. All the possible dynamics should be taken care of. It matches our voltage analysis too. It matches our model that in our understanding of the phenomenon that we're familiar with. So everything works out fine. It seems. Horizontal asymptotes, one thing, once again, as an exercise, you can describe this with the language of calculus. If you take the limit, okay, so let's take a look at the what happens after the limit. We have instead of a difference function, we have the derivative. Okay, so this one is not easy to solve, except if r is equal to 0, then it's easy, right? Right, because then we have y prime is equal to ky, negative ky. Okay, with k positive, and that's pretty much the same equation that we had with the population. So that's the difference, really. It's the same model, except the population it is only travels towards or away from 0, and the here at least whatever the room temperature is that is the everything converges onto that, which is understandable because the temperature itself, the number is made up. So this is Fahrenheit, this is Celsius, the number is meaningless. It is you can just as well declare this room temperature to be 0, and then you can have the same model. So this can be solvable, but once again, it takes a little bit more work to produce the same result with r, and when r is not 0, so we're gonna do this later. For now, we'll be just satisfied that it doesn't look that bad, and not like the last one. The last one had 2 terms, and it was much more of a challenge. Okay, so coffee. If we replace coffee with tea, what's going to happen to the graph or graphs?
It'd stay the same, right?
Not exactly. No. Well, there's a difference. Well, think about coffee and tea. I actually cannot tell, but the one of them is cooling down faster than the other. I'm not sure which one. But if it's different material, it has different properties.
So it'd just be shifted down or up.
No, the room temperature is the same.
Points per time.
Yeah, I guess, yeah. So they will be steeper or less steep, right? Yeah, so K, that's what's gonna change. K is the property of that material. Okay, so for different materials, depending on the way you do it, we'll produce different graphs. Some are very fast, some very slower, depending on so what's the fastest would be probably the air itself. If you bring the air in a cup, it will cool down very quickly. And in the meantime, something more thick would cool down slower in flatter. So I want you to see that modifying these models, once a basic model is written, then modify is very easy, and the modeling, the simulations are very easy to produce because the formula is still the same. I can modify it here. For example, it's very easy if that's the question here, number 35. What if we are gradually raising the room temperature? What's going to happen? So if you cannot guess, well, that's not shouldn't stopping you from studying, because all we have to do is just imagine that r is not constant in this formula, but rather some kind of sequence is growing. Okay, if that sequence is known, then the model is known, and therefore the model will be produced through the same formula with no extra effort. Okay, so you can certainly do that. Like I said, if you have that formula, you plug it into Excel or any kind of if you write code that you can do it with code. But if you can probably guess So if this is the room temperature, what's going to happen to coffee?
It'll
Well,
kind of have less heat.
Slowly rise.
And not less heat. You were saying it's declining and less heat.
It won't decline, but it won't. The temperature won't decline as fast as it would if the temperature stayed the same.
Initially, yes, but what's the end result?
Might.
Right, so it will stop declining, right?
It would cool.
It will cool to some temperature. And then we'll start to catch up with the room temperature. So quite a different model, but once again, you can discover that either from, like just using your common sense or modeling, and so you just a little Excel will produce, will make that picture. And from below, it will be growing faster, right? So if it is soda, it will be hitting. But so the language is the same, so that's interesting. The language is the same, it's an asymptote, except being a horizontal asymptote, we're having a oblique asymptote. So the bad news, so it works out so well, we can modify the system, we can replace tea with coffee, we can have rising temperature doing whatever we want. We have a heater there, we have air conditioning, and everything can work out just fine with at least modeling and simulation. But so the bad news, they can break down. The model can break down. So just because it looks so nice and convincing doesn't mean that it will always behave that way. Even on this level, when the equation is very simple and the model and the phenomenon itself is clearly well understood, it can still break down. So let me show you what can happen with the temperatures. Right, look at this. So no, this is not the temperature. This is about the logistic model. So once again, bacteria in a jar. Okay, so what's on the left is fine behavior. What I have to start to do is I increase K. Okay, in other words, the growth is faster and faster and faster. You can see what's happening. The original one, the left one is fine. Its K is equal to 20. We started with 2, I think. Okay, and then look at what happens. You see what's happening here in the middle. K is equal to 30. You see, I'm not sure it's you can see it, but look at how many dots I have on the left and how many dots I have here. Do you see what's happening? Where are the dots? What?
Farther apart.
You can't have farther apart. This is the time axis, so you have to have as many. They're missing because why some of the dots are missing?
They're above what the limit.
Right,
was.
exactly. Well, I'm not sure what happened here, actually. Now looking at it, there must be a point here. But this is clearly over here, the point is missing because it doesn't fit. It doesn't fit into the screen, and which means that the population is actually higher than the jar can accommodate. Which cannot happen. That goes against the model. It cannot have go about the size of the jar, and therefore if, and this is a really bad example, when K is equal to 40, jumps up and down, in and out. So in other words, it cannot happen. The system breaks down, even though the dynamics is still kind of makes sense in the sense if when the population is within the size of the jar, then it grows, but sometimes too fast and gets outside the jar, in which case it's too much and it goes down. And that's why it goes up and down, up and down. But it can never happen in real life, right? The bacteria, if this is how many bacteria can accommodate the jar, the population will never be larger than that. Okay, so the only thing is that the two parameters that really affect this kind of behavior is K and delta T. The rate of growth in delta T is the interval of time, and so if your delta T is too large and K is too large, then that's what you can end up with. Okay, so and that is really bad if you think about it. You want to rely on your picture on the left, and just because it does not contradict your understanding of the phenomenon doesn't mean that it is. Then what was the point? If you already understand the phenomenon, then you confirm it with the picture. That's fine. But if you want to understand the phenomenon that's new to you, and then you see picture on the left, and then you're thinking maybe it is just behaves well because the numbers are so nice, but my model will break down. So if I want to predict what's going to happen to the particular population, then I don't know. Maybe the system is fooling me, and it is totally possible. Okay, so that's the trade-off. That's what we pay when we do approximations. Okay, so it is an approximation ultimately, and so our understanding of the phenomenon might not match what model produces, and then you have to ask yourself: is it who is wrong here? The model is wrong, or our understanding of the phenomenon is wrong? Okay, so if there's the computational mathematics is very complicated. Okay, so you have to know all the calculus to begin with, and then a bunch of other stuff in order to how to handle numbers, how to handle errors. And this is not about errors, by the way. So if you assume that all the computations are totally correct, that will happen anyway. So then there are methods that ensure you that that something like that would not happen. We're not going to be doing that. So that's if you want to do it seriously. If you want to, do like weather prediction, yeah, that's the whole science. A few semesters of beyond differential equations that you have to deal with, and then some. But otherwise, this is also, it looks nice, by the way. Look at this picture. It looks nice. Another I chose K24, 25, H is equal to 0.05. The graph does not look too bad, but you see anything wrong with this? This is now, I switched from population now to the cooling. What do you see here?
It starts off cooling, but then it like dips below.
Right, which also, if we think about it, probably does not match our understanding of the phenomenon. So once again, it doesn't look too bad, but nonetheless, what's happening is not supposed to happen. So the answer is, if you want to, without thinking, make delta T smaller. Okay, so those dots close and close to each other, you probably will be. So you pay computational price for more accuracy in trying to prevent breakdowns. So it's a trade-off. Okay, so this is some algebraic proof here. How do you guarantee this won't happen? And there is a requirement here. I went through algebra. You can look through. So if K times delta T is less than 1, okay, so neither one of them is too large relative to the other, then what does it guarantee? It guarantees that there will be either decreasing or increasing, or in this case, it's decreasing. So the problem with this one is supposed to decrease, but it does not decrease and then increase. So how do we guarantee that the behavior is as required? And that's the requirement there at the bottom. If our choice of K and delta K is actually determined by the nature of the material. So K comes from the experiment. Okay, so we cannot really change that. But delta T is, delta T is what we can change. And as you can see, if K is large enough, delta T will be small enough in order to satisfy that requirement. So our model that is known to totally 100% to begin with, and nonetheless we have to have extra taken care of in order to ensure that the model that we produce will not misbehave. Okay, so it has to be that has to be less than. So if K is equal to 2, T has to be less than half. K is equal to 20, delta T has to be less than 0.05. Okay, so more than warning than really than anything else. Okay, so this is a model that we'll approach later. So it is the velocity of a flow along a pipe is given at each location in every moment of time. Okay, so this is as general as you can imagine. Okay, so location, if you know where you are and when you are, then you know which way you're going and how fast. Okay, so but otherwise, any flow within this pipe is possible, and the mathematics itself is very straightforward. If that function is known, you plug it in, time and location in it. You know the velocity. If you know the velocity, you move on and you find where you're going to be next in a moment of time, assuming that delta T is short enough so that you're not going to produce some weird behaviors once again. So if delta is small enough, it will be smooth transition from one location to the next as if it is a real flow. This is not very impressive because it's one-dimensional. Okay, so if you were to study flow on the surface, or especially three-dimensional, that's hydrodynamics and that is aerodynamics. These are the most complex things in the whole engineering, as far as I can tell. And so, this would be a starting point. So is airplane, how it flows and how the air goes around your wing.
No slip conditions.
What?
No slip conditions.
Fair enough. So this is really less than aerodynamics, because aerodynamics speaks of forces rather than velocities, right? So you have to, and we're not going into for now into the second derivatives yet. So it is way simpler. It's like And so the airplane is just standing there and just there are flow around it. So. Yeah, it is fair. It is not even approaching the complexity of the problem that you have to face if you want to predict weather or predict how an airplane would fly without actually building it. Yeah, so but it's starting. So delta y delta t is f of ty. That's the difference quotient expressed in terms of difference quotient, meaning velocity, incremental velocity expressed in terms of time t and location y. Once again, you take the limit, that's what you can produce. Well, before once again, take the limit, let's model it a couple of times. So here's some function f is picked. That function f depends on both, remember, both on time and space. Okay, so once again, blue is negative, x is positive, blue is negative, red is positive, and then you can see how you can confirm that whenever that curve passes through red, it's going up. Whenever it passes through blue, it's going down. Okay, on the edge, it probably stays, it goes horizontal. So you can see that, for example, what this spot over here, right? It is white. It's going through the white area, which means that it has to go horizontally in that area. Okay. So it goes slight pink, it goes up, red goes steeply over here. You can go up. So then producing a simulation model is no problem because it's the same exact formula done with any kind of simplest type of computer. But this is if you were to get rid of delta t and once again go back to our big assumption that actually the space is continuous, not incremental, and time is continuous, not incremental, then you have to do this. Okay, and this is the typical ordinary differential equation of degree 1, of order 1. Okay, so any function f might be there. So once again, any flow is possible hypothetically. So then you have to figure out what y is when it satisfies this equation. That's what E stands for, is the equation, such as x squared is equal to 3. Okay, so an equation that determines x possibly implicitly, indirectly. So x is there, but how do you find it? We are in a similar place here, but with by far, instead of looking for a number x, we're looking for a function f. Okay, so and then instead of just taking an equation, we have derivative of that function present. And unlike in calculus 1, on the right we have y. This is what makes everything really complicated. The present of y on the right. Okay, so that's what brings us outside of calculus 1 or 2. So if there is no y there, you just integrate with respect to t and you're done. Okay, so if you can pull it up. But with y present, that does not work. And so we have to invent methods in addition to numerical methods, quantitative methods. We have to invent analytic methods to solve it with some of these equations. Okay, let's summarize. So it's how to set up differential equation. So difference equation. So this is differential equation, and this is the well, any of this counts as the difference equation because it's made of differences. A differential equation refers to differentiation. Okay, so all right. So how there is a quantity y. So introduce variables as always. A number that represents the current state of the system that may change with time t. That's a typical situation. So variable, independent variable is time, just about every time. Okay, so we know that the increment delta y of y over standard interval of time is proportional to its length, delta t. Okay, so that's a typical situation. If it's not, then we really can not in the position to do anything with this. We'll produce a model that has a chance of being productive. Okay, step number 3. We know that the incremental delta y is also proportional to another quantity f that depends on the current time and current state. Okay, so like that flow, that in general, as general as it gets situation. And then in case of population, the delta y is proportional to y. Remember that. So that's what we're talking about here. Then we form a difference equation. This is it. Okay, delta y is equal to proportionality is right there. Some function that depends on time and space or location or state, and also the time interval. Okay, and then recursively defined function. I'm rewriting. I'm not producing anything new, because then y, what delta y, remember what delta y is, it's y plus 1 minus yn, that's what delta y is. So if I take this and rewrite it, I end up with this recursive sequence, which will produce one location at a time. You know where you are, you can compute your next location, you have a whole sequence. Done by hand or with the computer. Okay, so so that produces a simulation. Probably solve equation, but really what we produced is a sequence. And so maybe call it simulation. So one phenomenon that it probably includes infinitely many possibilities, and this we only do one at a time. That's the problem with computers. Okay. So if this is a continuous phenomenon being sampled, okay, so such as motion, flow, maybe not population, because it's usually changes incrementally. Then we use difference equation to form a different we form a difference quotient. Okay, so then that function f is not really a sequence, but it is now a function of the variables. Okay, and now it can be sampled now at any location at any density. That's the prerequisite for proceeding to the next stage and producing a differential equation. Okay, delta t goes to 0. How does it doesn't go, just go to 0 somewhere? This only works when f is given by a formula. So the idea that actually once or twice, the data might be fed into your system, and you can find the velocity and you can predict what's going to happen. But here, if you were to do it in this kind of traditional calculus way, you have to have a formula, because you end up with you start speaking of the derivative of that formula. Okay, from the left, and so that derivative, this is the ordinary differential equation, and delta t disappears. That's the good news. But now we have infinitely many values. It's like a whole rectangle of values instead of having cells that I showed you. Actually, it's defined and every single value of some kind of rectangle for t and t and y, vertical and horizontal, and then we're supposed to solve it somehow through really ingenuity. And sometimes it still fails. So that's efforts, and there's no solution there that is analytic in that sense. So that's called analytic solution. Okay, so so when we solve it when we're lucky, and how it means that I take that y, the formula substitute into the equation. I have two equations on the left and on the right equal to each other. Right, so if I have y prime is equal to y, I choose y is equal to et, then et prime is equal to et, and that confirms that the equation is true. It's that function satisfies the equation, to put it very simply. Okay, so just like you plug in, x squared is equal to 1, you plug in x equal 1 into the equation to confirm that everything is fine. And then when we're unable to find such a function in terms of familiar function, we go back to in circular fashion, back to the difference equation in our recursive formula in order to produce another recursive solution, which may or may not break down. So to watch out for certain things. Example, when it breaks down, even within calculus 1 and 2, you have an example of function that cannot be easily or explicitly integrated. E negative t squared. Okay, so it is not only possible, it is likely that the function that you produce will not be easily found, or might not exist. That's really the point. You have a condition that you impose, and then there might be, and you only have these many tools. So there's the exponential function, trig function. You want to combine them and produce a solution, and that works out if it's an equation that's created for you as a student in class, okay, and then there is a solution because somebody 200 years ago solved it. And so, but it's not really much of a luck, it's just what's called survival bias. Okay, so we can solve equations because we have the equation that we can solve. Okay, so practically speaking, you solve an equation in some real life situation, you probably don't have this luxury, just it's what's there. And so if you cannot solve it, you cannot solve it. So you cannot really go back, you cannot expect every time to find an analytic solution. Okay, so once again, difference between the calculus and differential equations is we know if we know when, we know how fast, and then we can derive where. That's simply integration. And now we're in a different situation that because what we have is if we know where, we know how fast. Okay, but how do we know where we are unless we know how we're moving, how fast we're moving? And so it's a little insoluble. Okay, so it's an equation, and that's why it looks so. So we'll get around it. Okay, so a bit of theory that follows, and that's to take the models that we have had, those discrete models in recursive formulas, and see what and just make sure that we have the language properly set up. Okay, so those sequences, what are they? What are they? We have a sequence of numbers, two, but the one of them represents, for example, location, the other one represents velocities. Okay, so we talked about that a little bit, so let's just clarify that. So it is literally called called discrete calculus, the simplest calculus of sequences. Okay, so it has two main operations, and that's the differences in sums, and that's what's delta and sigma stand for. Okay, so if you keep building, then you build more calculus, and then you take the limit, and you have the calculus as well. But if we were to stick to the situation which is inevitable when we do numerical things, then it's better to have this a little bit worked out and explain the setup and some terminology. Okay, so once again, the sequence of locations, the domain of that, you can, if you think of this, the function, that the domain is 0, 1, 2, 3. Okay, so moments of time, it's called, you look at the odometer in this case, or you look at the milestones, one moment at a time. Okay, so that's why the domain is made of points. Moments of time corresponds to points, and what is so special about points? They are zero-dimensional. That's why what we call this sequence a discrete zero form. Okay, so it's a special function which is with the domain, the discrete domain, as if it's just a sequence, and it is defined at points. Okay, so it is here. It is at 0, it is equal to 10,000. At 1 is equal to 10,500, and so on. Okay, so why it seems kind of complicated, a little bit unjustifiably, but if we move on to the velocity, we see that the difference between the velocities as we understand them and locations is significant because the velocity applies to the whole interval, not a moment of time. Okay, so on intervals here, I assume that during the first, say, hour, we were moving at 5 miles per hour. So it's an interval. Okay, and then this is also an interval thing. And so the velocity, I have three velocities. I have three locations, three velocities. So those 55, 40, and 60, I make a picture at the bottom to make that case that it does not apply like at the top, 1 moment of time. It applies to an interval of time. Okay, moments of time, intervals of time. And so intervals of time, it's one dimensional. Okay, it is so remember what dimension refers to. It refers to the number of degrees of freedom. So degrees of freedom is 0 point. You cannot go anywhere. If you have an interval or a line, you can move it back and forth, and that's only 1 degree of freedom. So it's one dimensional. Okay, the interval is one dimensional, and so we speak of the velocities, as you can see here, as as one forms. So a discrete zero form, discrete one form, and the relation between them is one is the difference of the other. Literally, that's the computation. So if you start with locations over there, you find that each of these four points, it produces three numbers for each of the three intervals. So that's the computation. It's called delta. Whether you divide by delta x or not, that's not relevant right now. Just take the consecutive differences and produce these sequences that kind of summarize what has happened. Okay, so that's another way to pay attention to is once again you observe the locations, and then taking what amounts to the derivative, you can summarize your velocities. It's summarize the trip with using, by the way, fewer numbers. So instead of 4, you have 3. Okay, so so on one hand, but then in reverse, that's where we are. This is still calculus 1. This is with differential equations, and calculus 2, primarily 2, is if you have the summary, can you find your location? So that's called integration. So it's not really differential equations yet. Okay, so let's provide the setup again. The setup for our where these two quantities live. We have the nodes. We have an interval, maybe infinite. Okay, it has nodes, possibly equally spaced. So just about every time in this course, we choose these nodes equally spaced, and then so that's one where one function can be defined zero form. These are zero dimensional. These are one dimensional is the edges between the nodes. Okay, so that's where the velocity will be defined. Okay, so so that's called, these are called cells. So if you want to go with the points, you can say node and edges. That's one way to say it. Another way, if you're aiming for high dimensions, eventually start counting the dimensions. So nodes are zero dimensional, zero cells. Edges are one dimensional, one cells. Okay, so this is, if you were to go beyond this, this is the high dimensional cells where things will be happening. Could be two dimensional or three dimensional. So the quantity, for example, what if we are what we spoke of temperatures, for example. Okay, so then our cells might be literally pieces of space, and then you're tracking the amount of the temperature in each of them. Okay, so then depending on what kind of space you're dealing with, you have to deal with the cells of high dimension. So it fits into the longer range of possibilities as we deal with them. And so these are the examples. So locations over time and other quantities are zero dimensional. Velocities are one dimensional. If you're looking at the pipe and you're measuring its linear density, remember from calculus 1, 2. So if sometimes that's a good example. Mass, linear density, mass when the independent variable is location, not time. Average velocity and the density, average density and linear density of a pipe. And then we can go what if it is a plate or it is a mass volume. Once again, all of these quantities require high dimensional cells. Okay, so but we'll stick to dimension 0 and 1. I think I'll stop here, and then so like this. I'll see you next time. Then